Okay, so I'll just label this exam 1 review. Okay, so the first question is to go over number 5 of the practice exam. Okay, so a mixture is created by isothermally mixing 2 moles of A with 5 moles of B at 25 degrees C. The equation below describes the delta H of mixing for A and B as a function of the final mixture composition. So delta H of mixing is equal to 15 times x1, x2. Assume that we have ideal entropy of mixing. So the delta S of mixing is in this case here, if it's ideal, the delta S of mixing is going to be equal to the R times the summation of xi ln of xi. That's what we covered yesterday or last week, I don't remember. Okay, part A. How much heat must be added or removed in kilojoules to keep the mixing process isothermal? So effectively what we have here is we have 2A moles of A and then 5B into a bin, and we're spitting out, right, whatever 7 moles of the mixture are. And the temperature here is held constant at 25 degrees C, which means that we're going to potentially have a Q term going either in or out of the system. So if we're to look at an energy balance on this process, right, we could think of this continuous if we wanted to, or we could think of it as a batch system. It really doesn't change things too terribly much. But basically, what we're going to have to figure out then is that the difference in enthalpy from this stream, these 2 streams, to this stream here, right, is going to have to be balanced out by the Q. So we know what the enthalpy change is going from the inlet streams to the outlet streams, because that's the delta H of mixing. So in this case, if we were to plug in the delta H of mixing, we would need to know that x1 is equal to, x of A, is 2 over 5, and xb is, 2 over 7, and this is 5 over 7. But it doesn't matter, it's symmetric, right? This delta H of mixing term is totally symmetric. So it doesn't matter which is A or which is B. So our delta H of mixing is going to be equal to 15 times 2 over 7 times 5 over 7. And let me check my solutions to see what the math of that works out to be. 3.06 kilojoules per mole. Times this by a total of 7 moles. 21.42 kilojoules. Now, we have a positive delta H of mixing. Does that mean we're adding energy to the system or taking energy out of the system? Right, so this is an endothermic process, so it's cooling down. So the way that we can look at the energy balance here is that the delta H of the mixing will have to be equal to, well, the minus Q is really how it kind of works out. It depends how we draw it. But let's actually go through the actual energy balance of the process here. I have it written down in my solution. So I did this as a continuous process here in my solutions. So if you looked at the solutions, my energy balance that I had was du dt is equal to 0, kind of treating it like I was continuously mixing these things, is equal to Q. Well, my solutions here are kind of a little bit funky here, but Q dot, integrated to Q dot, which is like the total Q you're adding to the system, plus 2A times by 0. I'm saying this is the H hat in of A in my solutions, plus 5B times 0. This is my H hat B in. And then minus whatever's flowing out of the system, 3.06 kilojoules per mole times by 7 moles. And this would be the H hat out of the mixed fluid. So also in the way that I did this here, the Q, I drew it going into the system there. So this term would go away, this term would go away. And then we move this to the other side of the equation, right? And we would get that basically, this is our Q. Any questions on that? So I'd say the main, I guess, kind of tricky part of the problem would be to recognize that I'm not asking for like the specific change in enthalpy, but actually you have to times it by the number of moles, and then also have to recall how we would consider the enthalpy of a mixture.
So
yeah.
I just have a question. Since we had a positive delta H, then wouldn't Q need to be negative because energy is flowing into the system?
So if it is, if we have a positive delta H, that means that the enthalpy of the mixture is higher than the enthalpy of the individual constituents, right? Which means that if I were to mix two things together, that you would have to give the system energy to allow it to be maintained at that same temperature. All right, so let's go over that one quick time. So I have the H of the mixture as a function of, let's say, x1. So you would be down here. This would be H hat 2, or rather H underbar. We could do it in molars. And up here, we could say this is H underbar of 1. Our ideal mixture follows this dashed line. In this circumstance here, we have positive delta H of mixing, right? So if I were to create a mixture with some given composition here in the middle, right, this is what we would have if it was H underbar, sorry, ideal mixture. There. This would be the H of the real mixture. So the concern, though, is that in order for these two fluids to be in contact with one another and mixed, they need more energy, right? They're going to a higher energy state. So if I were to mix these two things together in an adiabatic process, I would have to drop the temperature because you would have to take some of the energy that was individually stored in either component A or component B and give up that energy in the form of temperature, right? So it's dropping its temperature, cooling down its molecular motion, and it's converting that energy into the intermolecular interactions. Conversely, if we were to do this in an isothermal process, like what we're doing in the problem, you would have to give the system energy to account for that difference there. Does that kind of make sense?
Yeah.
But I know it's counterintuitive, so it's a little bit tricky sometimes, but that's kind of the gist of what we would do there. Okay. So were most people's concerns with problem 5 part A or part B? Probably part B? So part B in the problem asks, what is the exact word? Let me get it right here. What is the total Gibbs free energy of mixing for this process in kilojoules? So again, this is kind of just intended to be a bit of a plug and chug problem, noting that the delta G of mixing right, has exactly the same form as all the other delta G's, which is delta H of mix minus T delta S of mixing. So we have this one already worked out. The temperature is fixed isothermally at 25 plus 273 Kelvin. Anytime you see entropy, you should always think, oof, I better be working in absolute temperatures. And that the delta S of mixing is going to be this R times the summation of xi ln of xi. Oh. Yes. Is this has to be, is this minus? Where do I have where's my equation sheet? Drawing a blank here really quick. Let's see. Yeah, sorry, it's minus. I forgot that in the last slide too. Yeah. Because this, so xi is always less than 1, so that this term here is always going to be negative, so I need the negative here to make sure that the delta S of mixing is always positive, as a double check. And then, so then it just should be just a plug and chug from that point onwards. Then the last step is you'll have the delta G underbar of mixing, and you'll just need to times that by n, which is 7, to give the delta G of mixing in units of kilojoules. Kilojoules per mole and moles. Okay. Questions on number 5? So I would kind of classify 5 as a problem where you have to sort of draw in the definitions of the mixture properties and more or less kind of a not too complex in math, no calculus involved or anything like that. It's just kind of a grinded out type problem, just recalling all the different mixture definitions. What's the delta S of mixing, delta G of mixing, delta H of mixing? How do we apply these functions? Questions? General questions, quiz questions, exam questions, homework questions, anything else? Let's hear it. Yeah.
I have a question on 5. So
this one here, right? 5?
Yeah.
Okay.
In the statement it says that S external or something is 0. So
Oh, S excess?
Yeah, that is external.
That means the same thing as saying that the entropy of mixing is ideal. So we didn't have a chance to talk about excess properties this time. So the delta theta of mixing, this is equal to the difference between the theta of the mixture minus sort of the initial / unmixed. Right? So for most things, well, for anything that doesn't involve entropy, the delta theta of mixing is the excess property. But anything that involves entropy, we have to do a little bit different. So the theta excess is defined very slightly differently. This is the theta of the mixture minus the theta of the ideal mixture. So for the case of H, U, and V, this term is the same as this term, right? It's just sort of the weighted average, or in this case, the summation of xi theta underbar of I. So for enthalpy, volume, and internal energy, that's the case. So the excess properties for volume, enthalpy, and internal energy are exactly the same as the mixing properties for enthalpy, internal energy, and volume. But the difference is because the entropy for an ideal mixture here has this really unpleasant functional form we draw a deviation between the delta of mixing, which for entropy's case, even in an ideal mixture, is always positive, versus the excess property, which is really what makes our problems easier to deal with. So when we're dealing with real fluids, and if we're trying to characterize how two real fluids mix together, it makes a lot more sense to not worry about the calculations of an ideal mixture, because we can all do the ideal mixture calculations fairly readily. But the real concern is, what is the deviation from ideality? And that's where the excess property comes into play. But in essence, what I'm saying in the problem statement, assume ideal entropy of mixing. That means exactly the same thing as saying that the excess entropy is 0. But we didn't really talk about that too much. But okay, one second there. So those types of questions, though, shoot your hand up in an exam, right? I don't want some wording, details to hold you back. So the worst case scenario when you ask a question on an exam is I'll say, oh, sorry, I can't tell you that's part of the problem. Best case scenario is I'll resolve all your questions. But those types of questions there, I'll definitely answer that. Say, what's the excess entropy? So it means the same thing as this. Yeah.
Theta underbar of mixing, is that what we were calling before theta overbar?
No. So, okay. So theta, oops, my pencil died. Oh, there it comes, came back. The theta overbar of I is defined as dn theta underbar dni at constant temperature, pressure, and all the other things held constant, right? So this is how a material behaves in the mixture. The delta theta of mixing, and I vary where I put this, sometimes I put it by the delta, sometimes I put it afterwards. This is equal to the actual mixture property, right? So you notice that there's no subscript here. Minus, in this case here, delta is the xi theta underbar of I. So this applies for delta H, delta U, and delta V. Anything without entropy in it. So, but this term right here, this is the real mixture property. And this term here is initial condition. Right? It's sort of how much energy does component 1, 2, and 3, or so on and so forth, contribute to the mixture. Then the real mixture has sort of its own decision of what is the enthalpy or volume of the system, and that depends on the intermolecular interactions. So the delta of mixing, and so for enthalpy and volume, it's sort of really easier to visualize. In the case of the homework, if I add water and glycerol together, the volume is going to change ever so slightly. Right? So volume is not a conserved quantity. Mass and moles, those are conserved quantities, assuming there's no chemical reactions. But the interparticle interactions pack differently, whether or not it's a pure component versus a multi-component system, and so you might have slight volume changes, and those volume changes are typically going to correspond to different intermolecular interactions, so you're going to have enthalpy changes as well, which is going to be exothermic or endothermic mixing processes.
I actually have kind of a random question.
Sure.
Speaking of the velocity, not the velocity, the volume. So, I mean, is it ever possible that you get a large change in volume by at least 3 to 5%?
I think so, yeah. I don't think it should be too out of the question. So, for example, I would think that something that's dissociative might be along those lines. But I think I don't have a good feel for what's sort of the biggest volume change of mixing system. Certainly you can have exothermic processes that are so exothermic that they can be dangerous, right? For example, water and sulfuric acid type thing.
Sodium hydroxide and water?
Yeah, all those different, so those dissociative processes, those are extremely exothermic. I suspect there probably has to be volume change systems that are not quite as, the consequences are less severe. But the magnitude of which is the biggest, I don't know. In my mind, it's all possible, but I don't know what the limit of that is. What else we got? Any other questions? So on the practice exam, what were your guys' thoughts on the practice exam? Easy, difficult, straightforward, confusing? Everything? Straightforward? Everyone agrees? Very straightforward? So it should be a walk in the park on Friday, right? No problems? Okay, so what I can do is I can go into kind of a quick overview.
I have a question.
Yeah.
About one of the fugacity definitions.
Okay.
So for liquid, it's defined as its saturation times some correction factor, exponential, let's say exponential.
Mm-hmm.
So in those cases, how do we determine its saturation? Like we can find out fugacity from the other expanded with the Z form, and then do it for the liquid too. But in case we have to use the other definition, will you be giving us the saturation?
Okay, so the question is, I think, on the equation sheet, right?
Yes.
So the top line of the fugacity on the equation sheet, we basically have the definition of fugacity written out. So to start off, we have ln of F over P is equal G minus G ideal gas over RT. Now, in essence, this is effectively just the definition of fugacity. We're just arbitrarily defining it as a Gibbs departure function. Then in the equation sheet, we have a term right here, 1 over RT integral from 0 to P. 0 is the ideal gas state, P is the real state, V minus RT over P dP. This is how we would evaluate the fugacity provided we had an equation of state. Now, this term is not super useful because we don't generally have an equation of state that is explicit in terms of volume. Most of them are explicit in terms of pressure. So instead, we like to rewrite this in a slightly different form, which is Z minus 1 ln of Z integral V equals infinity, which is the ideal gas state again, going to V, which is the real fluid state. So this is the form that we would actually use, and we did use in the homework. Now, I have a continuous sort of equations being equal, being equal, being equal, right? And I write out this last equation. So I write the F of liquid minus equal to F saturation EXP 1 over RT P vape.
I have a question. Isn't Z minus 1 minus natural log of Z?
Yeah, I forgot that. You got it. Okay. So ultimately, if we have an accurate equation of state, we can use this expression here to calculate the fugacity of a liquid. The problem generally is that equations of state will typically break down for the liquid phase, in which case we will rely on the bottom expression. So the top expression is great because if we have an accurate equation that can predict basically the PV curve of a fluid, we can use that information to calculate the fugacity fairly accurately across the entire temperature and pressure range of any real fluid. Now, when we get to the liquid phase, then we kind of have this new breakout equation. This term, the saturated fugacity, we know is the same thing as the saturated vapor fugacity. So with an equation of state, we should feel reasonably confident that we can predict that accurately. The problem is, how do we predict the density of a liquid as a function of the pressure? And that's something that we cannot predict super accurately with equations of state. So this term right here is called the pointing correction. And if you recall, we derived a very similar expression for surface tension effects of small droplets. It had exactly the same functional form, just with some different limits of the integration. In general, this term is going to be small. So for the purposes of the class, I'll basically say whether or not to include it or not include it. And so I wouldn't stress out about worrying if you have to or don't have to include it. Right? So if I said something in a problem where a liquid gets pressurized to 1,000 bar, then you'll say, oh, okay, that's pretty high. Right? Or if you're ever uncertain and say, hey, do I have to include the pointing correction? I would definitely let you know if I'm intending the problem to be applied that way. But in essence, what the pointing correction is just basically integrating this expression, or rather this expression up here, for the real fluid. The ideal gas contribution has been integrated out, and you're just dealing with this expression right there in the liquid phase. So all the definitions apply, but all the different forms of the equation are just rearrangements based on convenience of what data we do have and what data we don't have. So I don't know if that answer your question, hopefully, with the Fugacity equation.
So we rarely use that equation. That's what you're saying here.
Well, so we rarely use it because if you actually crunch the numbers about how big of a correction this is here, because we can assume, let's say we're assuming that we have an incompressible fluid, right? We can pull the volume outside of the integral. And then we can just evaluate this expression to be V times P minus P sat over RT. If we were to actually evaluate what this term is, it's really small. So you have to go to fairly high pressures to have this thing move the needle. So for the most part, liquid properties are very hard to predict, but they're really not that variant. So in many regards, it's just easier to tabulate liquid properties as opposed to coming up with an equation of state that can predict all of them. So that's why we don't oftentimes use it, is just because you have to be going to fairly high pressures for this term to actually amount to something that is significant enough to throw off the calculations in any meaningful amount.
So that F saturation would be what we get from the previous equation, right?
Right, because the F saturation, right, the fugacities are constant across the phase change. So that's how you can get it from the previous ones. Okay. So we have about 20 or so minutes.
I have a question.
Yeah.
We talked about the last question on the quiz again with the maintenance cycle.
Last question on the quiz.
Or I'm sorry,
Okay.
the refrigeration cycle on the quiz.
Sure. What's the question?
Let me do that.
So to summarize, in the question I'm asking to draw the cycle on the, we have a pH diagram, label all the points, sort of identify some vapor-liquid equilibrium questions, and then one last question is, what is the work done on the compressor? So we have, let me draw this out really quick right here. We have an evaporator. We have an expansion valve. Then this goes into a compressor. We have a condenser. And that creates our full loop. We have heat going into the evaporator, and we have heat leaving the condenser. So can you recall what the question was exactly?
I don't have it with me. I only have the solutions online. Oh, this thing. This is, what is the temperature of stream 1?
Okay.
That's the first part.
So the question, what is
Give
the...
information. It's P equals 6 megapascals.
So the trick of this one here, so I said that the feed to the compressor, right, the feed to the compressor, stream 3, is a saturated vapor, sat vapor at minus 10 degrees C. And the condenser outlet, which is down here, the condenser outlet is a saturated liquid at 6 megapascals. And the question is, what is the temperature of this particular stream. We call this one stream 1. So, this is a good opportunity to talk about vapor pressure. So P vap versus T. You can also call it the saturation pressure, right? It's interchangeable. Now you'll notice that oftentimes in my problems or in the book, you'll see that you put a little T when you mention the vapor pressure. And that's kind of as a gentle reminder that the vapor pressure is an extremely strong function of temperature. And it happens to be exponential. We know it's always exponential because of the Clapeyron equation, or the Clausius-Clapeyron equation, whichever one you want to think of that. Now, what the vapor pressure curve tells us is that if I am in a saturated state, meaning that I'm either two-phase or about to be two-phase, I cannot independently vary the pressure and the temperature. Otherwise, I will be leaving the two-phase region. So the key here is the term saturated in both of these circumstances. Because if it's saturated, if I give you either the temperature or the pressure, you must be able to find the other one without any additional information. It is an innate material property of the system. So in this case here, let's say, for example, if we start off with the saturated vapor at minus 10, in essence what I'm asking for is if this was minus 10, I want to know what is the pressure at minus 10 in order to be saturated. Likewise, as the saturated liquid at 6 megapascals, I'm asking for up here, if this is 6, what does the temperature need to be in order to satisfy that I'm in the saturated state? And so in this particular problem, you were given a diagram. In this case, it was a pH diagram. But I'm hoping that all these diagrams are getting easier and easier to read. All you need is 2 pieces of information, but there's lots. Right? In this case, the two-phase region generally always looks kind of like a parabola type shape. I don't think I've ever seen an engineering diagram where that doesn't seem to be the case. And then we have constant temperature lines in this one here that kind of go down and go straight, down and go straight. And so a couple of key characteristics that you can look for when you're looking at these engineering charts with the two-phase region is flat lines in the two-phase region, because that tells you that the temperature and the pressure is constant. And there's also entropy curves and things like that. So a couple of identifying features here. What is this called? Critical point. It is the end of the two-phase region. So what is this point right here on the axis? Critical pressure. And then if I were to draw this temperature line, that just kisses it right there, that is what? Critical temperature. So in the problem, the issue is just either in this stream right here, we are dealing with a saturated vapor at minus 10. So the key here is you would find whatever line corresponds to minus 10, and then look up whatever pressure that happens to be at. And then conversely, for this one over here, you have a saturated liquid at 6 megapascals. You would start off here at, let's say, 6, and we know that this is the saturated liquid enthalpy, and then we would have to basically interpolate between these two. Now, if you have the solutions in front of you, I drew this wrong. This is actually up here, I think. But the same thing holds true. So you're given 2 pieces of information, and that the intersection of those 2 pieces tells you everything else you need to know. Piece 1 is your pressure is at 6 megapascals, and piece 2 is your saturated liquid. So 6 megapascals pressure, saturated liquid, which means we're on the liquid side of the saturation curve. That gives us the intersection of 2 lines, 1, 2, and at the point there, then you read everything else off. So it doesn't have to necessarily be, 2 lines of information. Right? Just 2 pieces of information on an engineering chart will lock you down in a particular position. Okay. So I'm going to rattle off just some topics as reminders. Yeah, okay, go ahead.
So point 2 is on saturated liquid line or inside the
Okay, let's see. So basically, just to finish off the problem. So let me just label these points really quickly here. So this is called 3, this is 1, so this is 2, and this is 4. So your question was what again?
point 2?
Point 2. Where is point 2? Okay, so on the problem statement, this is the expansion valve. And it said it's ice enthalpic, meaning that the delta H is 0. So in this problem here, we are a saturated liquid at 6 megapascals. And so reality in the actual solutions, I think it's like right here. Let me just change it to a different color so it stands out a bit. We're right here. So we know that whatever happens going from state 1 to state 2 has to follow a path of constant enthalpy. So that means we can either go up or we can either go down. So we don't really know exactly right now at the moment. But we know that this is a cycle, so everything has to connect back to one another. So we can work ourselves around basically whichever manner we want to do. So step 3 is a saturated vapor at -10, and so actually for that case, it ends up being something right here. So the only way that we can cause these two lines to connect is to then draw this line to go down. Now, truth be told, we don't exactly know how far to draw it down, so we have to look and work from point 3 backwards a little bit. Going between point 3 and point 2, it says that this is isobaric, so it's constant pressure, which means that this one can only move on this path over here, so it makes sense, obviously, then that we should connect these two dots going this way there. Lastly, just to wrap this up, the going from, let me label these, so this gets confusing after a bit. This is saturated liquid at 6. Okay, this is 1, this is 3, this is 2, and then some point 4, we don't know where it is yet. So going from 3 to 4 is isentropic, and so the constant entropy lines actually end up going something like this, and going from 1 to 4 is again isobaric, 1 to 4 isobaric, and so then we connect the dots like that. Yes?
And then to get the work or the power done by the compressor, now that we have these points, we can read the enthalpy off the diagram
Yep.
at each point, and we just subtract across the compressor.
So the compressor is going from 3 to 4. So the energy balance on the compressor, right? Let's just do it really quickly in our head so that this doesn't become a burden. I don't want, in my solutions, I oftentimes do the full drawn out energy balance, but I don't expect that on the exam necessarily, right? So in this process, it's open, it's steady state, it's continuous because it's a cycle, so everything has to keep going forever. So we have energy coming in stream 3, we have energy coming out in stream 4, and we have energy coming in terms of work. So ultimately we have 0 is equal to H3 minus H4 plus W. So that W is equal to H4 minus H3. Here we have H4. Here we have H3. Noting that this we could draw under bars here, whatever the units need to be to make this work out. So the last part of the problem was just differencing these two enthalpies at the bottom right there.
So whenever we see expansion curve, does that mean isentropic process?
Generally speaking, yeah. So the reason why we make the assumption that the expansion valve is isenthalpic is because it's a teeny little piece of equipment. It's just a valve. And so if you think about it in terms of the reference of, the valve, right, it's always there and there's always material going through it. But if you think about the reference as the fluid, it spends such an infinitesimally small time in the valve that there's not enough of an opportunity for it to be taking on or giving away a lot of heat. So that's why we generally make the assumption that it's going to be isenthalpic, because there's not enough time for that unit operation to cause energy loss, right? Because the fluid's just blasting right through it. So in terms of like heat transfer, you need to have surface area, temperature gradient, and you need time. But there's no time, so it just very rapidly goes through it. So when you think about the fluid itself moving through the system, there's just no mechanism to have a lot of energy go in or out of the system. And so that's why a valve like that is typically going to be assumed to be some sort of an isenthalpic type valve. But it doesn't necessarily mean it's going to be isentropic or anything like that, right? But the enthalpy of the fluid is going to depend highly on, basically, it's the heat in and heat out. Now, in the case of a real fluid and a real refrigerant, right, the enthalpy does have to change as a function of pressure and things like that. But as a general sense, yeah, for the cases of the refrigeration cycle, you want to design it to be isenthalpic. This is an ideal circumstance as well. Okay. So let me just refresh ourselves in what we've done before. So in chapters 3 and 4, we talked about energy and entropy balances. So remember, all of these problems are solved by simplifying one of two equations. du dt is equal to the summation of m dot h hat of k. In this case, k corresponds to the different streams going in and out of the system, plus q dot plus w dot. Likewise, we have the same expression for entropy. Oops, this is an S. Okay, what happens when the system is adiabatic? Q goes to 0. What happens when the system is reversible? S gen goes to 0. What happens when we have a closed system? These go to 0. Okay, what happens when we have a steady state system? These all go to 0. Piston cylinder device, open system, adiabatic system, reversible system, closed system. All of them start off with these two equations. So let's say, for example, we are working with a system that is closed and we want to simplify these expressions. So if it's closed, our energy balance simplifies down to du dt is equal to q dot plus w dot. Now, let's choose any arbitrary piston cylinder device. Let's say we change the volume. Let's say we change the temperature. Let's say we change the pressure. I'm going to do a really simple trick here to handle all of that. I'm just going to integrate it from state 1, right, where state 1 corresponds to temperature 1, pressure 1, specific volume 1. And I'm going to integrate it to state 2, which is temperature 2, pressure 2, volume of 2. Now, in the case of the left-hand side of the equation, this just goes to delta U, which is equal to U of state 2 minus U of state 1. So for any state property, all I care about is what is my final state and what is my initial state. And I know that U of 2 is a function of temperature 2, pressure 2, volume 2, and that U of state 1 is equal to temperature, is a function of temperature 1, pressure 1, specific volume 1. Now things get a little bit trickier for the left-hand side of the equation. Generally, we can just integrate Q and say, it's the total Q. Right? Either it's something we're solving for or it's something that we're given. Now the work term, this one requires a bit more work where you really have to choose your path correctly. Right? And typically we're going to write this as PdV or minus PdV.
For Q, at least on delta U, wouldn't it be common just to work with like CV, DV? Because you look at Q.
If you're talking about an ideal gas, then sure, yeah, you can easily substitute the delta U to be C sub V delta T. But in reality, you would actually want to do delta U is equal to the integral from T1 to T2 of C sub V dt.
That's what I meant right there.
Yeah.
It's just,
But this is really just based on the definition of C sub V. So the key thing to keep in mind is that we have arbitrarily defined C sub V and C sub P as a way to just categorize and store data because we don't have a way to predict it. So all the C sub V and all the C sub P information we have, that's actually something that we've come up with. Okay. So let me move on very quickly here. So then we kind of brushed over chapter 5 in the book with cycles. We kind of picked up that along the way. Chapter 6, this was the combined first and second laws. And effectively, this is where we derived this expression. Right, so this equation right here, all this means is that if you satisfy this equation, you're never going to go wrong. You're never going to make a mistake. Because all this is saying here is that you're conserving energy and entropy is always being created for any process. That's what this expression means. So we manipulated this in a number of different excessive ways, right? Expanding it, for example, saying that du, just using general calculus terms, is du ds at constant v ds plus du dv at constant s dv. Right, so we expanded this, we came up with thermal identities, we derived new functions, we manipulated the variables, we played around with a lot of different things, right? We came up with Maxwell relations, thermal identities, right? All this sort of fun stuff. All we did is just took the first and second law and essentially the Gibbs phase rule and manipulated it with general calculus relationships, right? So we didn't ever talk about what is an equation of state, right? We just kind of generally said no matter what functions we put into here, right, the fundamental theorems of calculus will take care of it for the rest of it. But the whole reason why we did this is we have the internal energy, which is kind of an important quantity, in terms of the entropy and the volume. That's not terribly useful for us. So the whole point of all of this was to take the first and second law, which is the foundation for all of thermodynamics, and transform it into new variables that we can actually use and manipulate in the real world with variables that we can actually easily measure. So the ultimate goal was to derive essentially this expression here. We started off with TdS minus PdV, and put little underbars here. This expression, not helpful. It's great for starting derivatives out because it is the basis for all of thermodynamics. But in reality, we'd much rather have an expression that looks like this. As I'm saying it out loud, I'm sure you don't want to deal with an expression that looks like this, but in terms of practicality, it is much easier to manipulate. What we've done is we've taken the basic fundamentals of thermodynamics and we've converted it into an expression of things that make sense to us. I understand what specific volume is. I understand what pressure is. I understand what temperature is. I understand what heat capacity is. The only thing that we need here is an equation of state that relates temperature, pressure, and volume, and data. Real fluid data of that particular material. Then we did exactly the same thing with dH and ds. You know, we could do the same thing with dG and dA. So the whole point of chapter 6 was to take the basic fundamentals of thermodynamics and expand it and manipulate it so we can get it into variables that we can actually understand. It's a lot of math just to get to that end goal of just allowing us to understand what is going on. As it turns out, enthalpy, my pencil just died. Enthalpy is exceptionally important and useful for open systems. As it turns out, Gibbs free energy is exceptionally helpful and useful for multi-phase systems. Right? So these are all variables that we have arbitrarily defined. And then moving forward, effectively what we're doing then is just building up new variables and new functions that we think are useful to help us solve real problems. And that moves us on to multi-phase and multi-component problems, where we say that across a phase change, delta G is equal to 0. And this gives us a new layer and a new tool of things to build and manipulate. We've already kind of talked quite a bit about phase diagrams, so PV plots and isotherms. So obviously that's something that's important. We talked about it quite a bit on the homework. We defined fugacity. Again, fugacity is another unit of convenience. Now the problem with the Gibbs free energy is when you go into multi-component mixtures. The fugacity for pure fluid mixtures is really not all that necessary. It's kind of a convenient framework, right? Because it's a unit in terms of pressure, which kind of makes sense to us intuitively, whereas the Gibbs free energy is this magic energy term. But ultimately, we don't need fugacity to solve single component phase problems. We need fugacity to solve multi-component phase problems, because if I add one molecule of, let's say, material A to an infinite C of material B, this A molecule, its entropy has shot up to infinity. And so the problem is when you're trying to do these basic fundamental phase calculations, it makes it really difficult to deal with infinite numbers, right? Because in many ways you have an infinite gain of free energy when you mix two things together. That's not super useful to solve practical problems if you're always dealing with going to and from infinity. So the fugacity is defined as the deviation between the real fluid properties and the ideal gas property. And so then this concept here of going to infinity gets washed out, because that happens for ideal systems. But in essence, all that we're doing up until this point in the class, right, is we've just taken the first and second laws and we've just made up functions, basically, that happen to be useful for real calculations. But it seems a lot more onerous than it really is, because I think if we were to start off from the basis and rework everything, we could kind of sail through a lot of material to get to that point. But it does involve a certain degree of abstraction, just allowing yourself to say, okay, I don't understand what fugacity is, but you have to understand that it's useful and know how to apply it. Because in many regards, right, this is not a super intuitive discipline. There's not a good way for me to close my eyes and visualize what fugacity is. It's just a function that turns out to be super useful. And that when thermodynamics was developed in sort of the mid to late through the early, mid to late 19th century into the early 20th century, right, there was a lot of pushback for kind of these abstract concepts as well. And so this was a period in science development when sort of the old school folks, they resisted any effort to move away from something that you couldn't think or hold or touch or feel or measure in a lab, and moving more towards a mathematical framework, which then ultimately transitioned into statistical mechanics, and then quantum mechanics, which really just took it and ran with it, and you can't visualize anything with quantum mechanics. Like the wave function. The wave function is inherently a meaningless term until you manipulate it, and then it becomes magical and tells you everything about the system. All right, there's my pep talk. So everything is artificially constructed, but it turns out that we've constructed it in a super useful way to solve real problems. Just keep that in your heads. All right. So unless there's a super pressing need, I won't hold a help session tomorrow, but, stop by maybe in the afternoon if you have a question, and I'll see if I can help you out. Okay. See you all on Friday.